Hello everybody, my name is Massimiliano d'Aquino. I'm with the Department of Electrical Engineering and Information Technology at University of Naples Federico II in Naples, Italy. And today I'm very happy to present our joint work on chaotic dynamics and thermal switching in AC-driven nanomagnets. First of all, I would like to thank the organizer of the conference for the possibility to present our work here. Thank you, Giovanni. And I would like to briefly introduce the co-authors of the presentation, who are Salvatore Perna, now who is assistant professor in our group in Naples, and formerly was PhD with us. And then there is Claudio Serpico, with whom I have a very long-lasting collaboration since many years. First of all, let's give some motivation for this work, and this is based on the importance of magnetization switching for a number of applications, like classical one like high-speed and energy-efficient recording devices such as hard disk drives and magnetic random access memories, where the design is constrained in the framework of the so-called magnetic recording trilemma, coping with desired large information density and small volume and larger thermal fluctuations which affect the thermal stability of the particle. And if you want to increase the thermal stability, you have to increase anisotropy, but then you need stronger excitation to switch the memory cell. And so lately, several strategies were proposed to circumvent this issue, such as microwave-assisted switching, which is in the framework of the more general energy-assisted switching, where an external action, typically AC, is applied to soften the magnetized bit, which can be reversed with the DC action, like a field or a current, which is significantly lower than the classical threshold in the absence of the external action. Very recently, the use of bistable units for low power computations was proposed in the framework of the so-called probabilistic computing, and it was shown, like in this nice reference here, that superparamagnetic perpendicular and in-plane magnetic tunnel junction can be used to implement p-bits, namely magnetic elementary switches with switching probabilities which can be tuned with the use of an appropriate bias, which may be a current or a field. So let us briefly recall magnetization dynamics in uniformly magnetized nanomagnets. Everything is described in terms of a small m vector, which is the magnetization unit vector, arising from normalization of magnetization by the saturation magnetization at a given temperature. This will imply the fundamental constraint that the dynamics of the normalized magnetization occurs on the unit sphere, which is our state space. And this magnetization dynamics is expressed as a Landau-Lifshitz type equation, whose right-hand side can be expressed in terms of two scalar potentials. The potential G, which has the role of magnetic free energy, including shape, magnetocrystalline, and Zeeman interaction. Here we emphasize the presence of a time-varying applied field. And non-conservative effects are described by another potential psi, which describes the damping terms and the spin torque, for example, controlled by the normalized injected current beta. So in the conservative limit, where psi equals 0, we can represent the precessional dynamics on the unit sphere. All the trajectories are periodic and filling central regions around energy minima and energy maxima. So in the present case, we will have two minima along the x-axis and two maxima along the z-axis, separated by special trajectories starting and ending on saddle points on the y-axis. And these are the heteroclinic trajectories. In order to study magnetization dynamics driven by AC excitation, we introduce a perturbation technique. So we write the Landau-Lifshitz equation in this perturbative form, and this is possible since the damping, spin torque, and AC field pumping in situation of technological interest are small quantities of the dynamics. So with this epsilon, we will refer to the order of magnitude of each one of these terms. So, in this framework, the Landau-Lifshitz equation can be seen as a non-autonomous dynamical system that can be analyzed by introducing the stroboscopic map. So, basically, we will sample magnetization after each period of the external excitation. So, this n will be the index of the number of periods that we are analyzing. And it turns out that the stroboscopic map, this map which depends on the epsilon parameter, can be developed in Taylor series, and the zero order term is very similar to the unperturbed phase portrait of the Landau-Lifshitz dynamics, this one, which is represented now in cylindrical coordinates. And then the derivative of this stroboscopic map can be amenable of analytical treatment, which we will see in a minute. So what we can say is that the Seddel fixed point of the unperturbed map coincides with the Seddel equilibrium of the conservative dynamics, and these will be connected by special heteroclinic trajectories connecting the two Seddels. So we can see these trajectories named gamma 1, gamma 2, and when you perturb these dynamics, the Seddels are structurally stable, so will persist, but this heteroclinic connection will break due to the symmetry breaking, and a kind of so-called stable and unstable manifold will be created, which are invariant sets, meaning that if you start from magnetization lying on this manifold, then you will stay on this manifold forever as the index n goes on. So we can recognize two limits. So if the epsilon is rather small, we have the damping dominated dynamics in which no intersection between the stable and unstable manifold of the map occur, and so there will be a kind of distance between the two manifolds. So the stable one, which means that it tries to attract magnetization regimes to the Seddel, and the unstable one, which tries to distantiate magnetization from the Seddel. These two manifolds will have a splitting, which we indicate with D, and if we increase the amplitude of AC pumping, what will happen that eventually there will be an intersection, and an heteroclinic intersection, and forward and backward the map iterates must belong to both stable and unstable manifold, and this is possible only if there is a complex entanglement of these curves, which creates a very densely packed manifold which has a fractal structure. So it tends to occupy all the state space as far as you increase the AC pumping amplitude, but of course to preserve the fact that you must have an infinite number of intersections. So in this framework we can recognize some structures termed lobes, which can be of capturing or of escaping type. The capturing lobe is a lobe that starts outside the region surrounding a stable equilibrium, and is able to attract phase points inside. So capture magnetization dynamics and, for example, bring magnetization towards one of the equilibrium. And on the other hand, can be of escaping type, so it can capture magnetization regimes within the basin of attraction of this, for example, equilibria, and bring out, so realize an AC-driven switching, and this will occur in a chaotic manner. The analysis of this heteroclinic tangle phenomenon can be performed analytically in the framework of the perturbation technique that we introduced before. And here I don't have enough time to tell you all the mathematical details of the treatment. I can tell you that everything is based on the unperturbed phase portrait of the dynamics, and by using appropriate perturbation technique based on the Melnikov function, so-called Melnikov integral, we are able to end up with an expression, an analytical expression as function of frequency and polarization of the external excitation, which is related to the onset of the heteroclinic tangle. So we can know exactly, given the dimensions, material characteristic of the particle, which frequency and polarization are required to create the heteroclinic tangle. Now we introduce the concept of basin erosion and particle escape from a potential well. So basically we consider the Landau-Lifshitz equation for a large number of particle replicas. This large number will denote by n, and each particle starts from an initial state, a black dot represented on the state space in cylindrical coordinates, which fills the energy well around a given equilibrium. So let's say mx equal +1. Then we will integrate for a total time multiple of the period of the AC excitation by this small n. And at each iterate we will remove initial states corresponding to particles with energy that exceeds the Seidel energy. So at the end of the story, after n iterates of the map, the regions will be filled with black dots representing the portion of the basin which is safe from the erosion. And the numerical simulation confirmed that the erosion starts as far as the heteroclinic tangle is appearing. So we report an example of under microwave field linearly polarized along the y-axis, so the transverse axis of the particle, and we will check the number of particles escaped on the overall number of particle replicas, and we can see that as function of frequency we will have a degree of erosion which is very large, close to 1, well below the FMR frequency. So this is a broadband basin erosion which occurs far below the FMR frequency. And details are reported in these references, and you can see that the complicated patterns of erosion appear in the basin of attraction of the stable equilibrium along the x-axis. The heteroclinic tangle and the basin erosion can be used to understand the thermal activation under AC excitation. First, let's recall what happens under DC excitation, and we know that the thermal transition time is given by the celebrated Néel-Arrhenius formula, which is expressed in terms of the ratio of the energy barrier to overcome and the thermal energy, and in terms of the attempt frequency, which is the reciprocal of this tau zero. And basically it represents what can happen at the bottom of the potential well, and eventually there is a number of times that the system tries to overcome the barrier, which is given by the attempt frequency, and then the difficulty of jumping over the barrier is given by the energy barrier. Under AC excitation, there is no trivial extension of this formula, but we can demonstrate that there is an interplay between thermal activation and chaos, because the chaos occurs in the region close to the separatrix curve. So it is like the heteroclinic tangle will create a chaotic region at the top of the potential well, helping the particle to jump over the energy barrier. So, and our point is that the onset of heteroclinic entanglement has measurable effect on the thermal transition statistics for superparamagnetic particles. So let's have a look to the AC-driven magnetization dynamics in an example case. We have seen that depending on frequency and amplitude of the external excitation, in the specific case there will be a field linearly polarized along the y-axis at a given frequency. At zero temperature you can see that for a given amplitude of the AC field in normalized units, there will be a complex fractal erosion of the basin of attraction, but there will be a safety region which is continuously filled by black dots around the equilibrium state, which is this red dot. And if we play a little bit with the stroboscopic map, and we will compute it by setting the temperature to non-zero values, we will see that all these complex features of the entanglement will blur somehow, but the safe region around the equilibrium will be quite stable with temperature. So we interpret this situation as the fact that we are reshaping somehow the energy landscape by applying the AC excitation, and so now we have to compute the thermal transition with respect to the boundary of this pseudo well created by the AC excitation. So this conjecture was eventually demonstrated by performing experiments on superparamagnetic magnetic tunnel junctions. So a magnetic tunnel junction consisting of a synthetic antiferromagnet reference and a superparamagnetic cobalt iron boron free layer separated by an MgO tunnel barrier was considered. And the random telegraph noise signals were measured by Eric Montoya and the group of Ilya Krivorotov at University of California, Irvine, and this was done as function of amplitude and frequency of the applied AC voltage to study the dependence of the thermal transition rates on the external excitation. The results of the measurements were compared to our analytical predictions, and eventually they fit very well. So everything was published in this paper in 2019. So let's recall the main points of these experiments. Here we have the schematics of the measurement system with the sample here, and the source and the instruments which measured the random telegraph signal. This random telegraph signal is measured in the form of a variation of the resistance in time of the structure. You can see that resistance is switching randomly between two distinct values. This is a measurement at zero applied voltage. And here there is the measurement at a given non-zero AC voltage applied to the structure, and you can see that there is a threshold behavior of this phenomenon, and after exceeding a certain microwave power applied to the sample, the switching rates start to explode, and so the frequency is becoming higher and higher, and this can be related to the deterministic chaos that we predicted. And if we compare the prediction that I showed before, we can see that there is a very broadband frequency range where spanning over several gigahertz, where deterministic chaos appears to be the main mechanism governing the nonlinear magnetization dynamics. Of course, at lower frequency, the role of fluctuation becomes more important, and so the measurements deviate from the analytical theory, which is purely deterministic. I want to stress this. And above a certain frequency, as far as we approach the FMR frequency, the latter becomes very important, and of course also here we have some deviation from the purely chaotic prediction that we presented. So we can interpret the AC-driven dynamics in terms of reduction of the stability margin of the equilibrium state. So here we represent a cartoon with the directional map of the probability that magnetization is initially within the one potential well, and the probability to remain in that potential well after 5 periods of the alternating spin torque drive. And you can see that in the absence of voltage, of course, this is all filled by all the phase points, and in the presence of an AC voltage but at zero temperature, you will have a complexly entangled structure related to the heteroclinic tangle that we see before. And when we set the temperature on, of course this can be done in simulation, but it happens also in the real experiments. All these sharp tangles are softened somehow, but the safety region is quite robust with respect to temperature, and of course produces a probability close to 1 to stay in the safe region. So this was the final message of this presentation, and here now I report a summary of what we discussed, which may be useful. Some references to reconstruct all the story. And last but not least, I would like to thank you very much for your attention.